All right, I think it's time to get started. Good afternoon, everybody. My name is Joakim Lindh. I work at a company called Texas Instruments, where I lead our software applications team, helping out customers worldwide to develop IoT products, specifically within wireless communication segments. I am here today to talk a little bit about wireless communication and the dark arts of wireless communication, sort of. A friend of mine asked me the other day what I was going to talk about at this conference. And I said, well, I'm going to talk about wireless connectivity. And he was like, okay, but isn't that a software developers conference? And I said, yes, it is. So we'll see how this actually goes. But in general, I mean, the information age that we live in today is actually based entirely upon the physics of electromagnetic waves, as you will see. Constantly, every day, we get immersed by all these signals, the wireless communication solutions around us. And most of the time, we don't appreciate or understand the complexity behind it and all the things going on around us. And don't get me wrong, I don't mean to say that everybody needs to understand this, but I think for people who work with IoT products should probably have some knowledge about what is actually going on. So I hope you understand a little bit better what is going on after this session. And it might be traces of unicorns and fairy dust and other unimaginable things throughout this talk, but most of the stuff is actually real, most of the stuff. So, today we have this global interconnected world. We had the internet, and now today we have the Internet of Things, which is sort of something that not even the most visionary engineers couldn't even grasp 30 years ago. So it's really hard in terms of what to expect in the next 15 years when you talk about these kind of products. Today we are approaching something called system of systems, where all devices become interconnected in some way or another, which is defined by Internet of Things. I tend to keep things simple, so I tend to define the Internet of Things as the digitalization of the physical world. Now, this means that you have some sort of device. This might be a sensor or a beacon that is measuring data, temperature, recording video, whatever. It has some sort of data that is useful, that is important. This type of data is sent through some sort of network up to a more capable device. Now, if you're using wireless standards such as Bluetooth, Bluetooth Low Energy, Wi-Fi, the network in this case would be your smartphone. If you're using cellular standards such as 4G, NB-IoT, GPRS, the network would be a cellular base station. Or it could be an entirely proprietary protocol. A good example is the startup Disruptive Technologies that had a talk the other day. So there's different types of way of going through this network up to a more capable device as we today define as the cloud. Now, the data itself that is collected isn't really that useful until you make something out of that data. And that's what the cloud is about. That's the part where you actually take all this IoT data, you transform, enrich, you filter it, because IoT data contains a lot of noise, a lot of gaps, and a lot of false readings as well. So in the spectrum, on the device, on the edge side of things, we have a lot of constraints. If you've seen some of the other IoT talks, you know that we're constrained by limits in terms of memory. Maybe it's around 100 Ks of flash that the entire operation is going to run on. So we have a lot of constraints when it comes to the device, while in the cloud, we have virtually unlimited processing power. So, how did we end up here? Why is IoT such a hype anyway? The wireless communication is the focus here today. So I'm not going to continue to talk about the cloud side of things. We're going to focus on the radio communication. But to put things in perspective, IoT has three things to be grateful for when it comes to its success. So there's three main things that act as a catapult when it comes to the Internet of Things. The first thing is the power efficiency, that we're actually able to create awesome IoT products that can truly operate in really low power. It means that these devices will actually remain in some sort of sleep mode, maybe just consuming a few microamps, maybe nanoamps, and just wake up only when needed to transmit just the right amount of information. In terms of size, this product has become a lot smaller. So what you had today that would fill up this entire room can be fitted in just a few centimeters. In fact, the complete design with the wireless MCU, the radio front end, the sensors, everything, is actually smaller than the actual battery powering the device. So things become truly small, and it's becoming even smaller. And the last one is obviously cost. Cost is reduced significantly. If you've seen the other talks at this conference, you know that these devices cost around $1 or a bit more. So it's becoming really low cost to add connectivity to a product, whether it's a coffee machine, refrigerator, connected toy, whatever the type of product. So let's take a look at the architecture. Let's take a look at the fundamentals when it comes to RF communication. So we have some sort of transmitter, we have a receiver, and we have a channel in between. Historically, that might have been a cable or something. In terms of wireless communication, it could be sonic, it could be an optical channel, it could be infrared, like the old remotes that we used to have back in the day. You don't have those today, only with the cheap TVs, but with the more, let's say, medium, expensive TVs, we actually have radio communication. So RF radio is becoming a standard that is taking over from a lot of these historical channels that we have. So we will focus on radio frequency. So we have some sort of transmitter. Now, we're getting into some of the technical aspects, but please note throughout this presentation, I'm trying to simplify things as much as I possibly can. So we have some sort of data, low frequency data, that we put onto a high frequency carrier. We modulate the signal, and don't worry, I'll explain this stuff later. We modulate it, we send it off to a piece of metal, which is the antenna, that radiates a signal that creates the data being transmitted over the air. And at the receiver side, since we've lost a lot of energy through this channel, we're losing huge amounts of energies. We need to have a low noise amplifier to amplify up the signal, demodulate it, and we get some sort of estimation out of this. Obviously, from a user perspective, the data is usually the same. And these devices are typically have both a transmitter and a receiver in the product. So it's a transceiver. And today, most of those are software configurable, fully software configurable, which means that you can run different types of radio protocols. You can have one chip that solves the problem in a Zigbee network, a Bluetooth Low Energy network, Wi-Fi network, a lot of different protocols. So it's becoming more software configurable, which means that you can update products in the field to support new type of network topologies. So let's get into some fun stuff. Let's get into the dark side of things. Actually, it's not that dark. The first version of this presentation even scared me, to be honest. So wireless communication and the concept of RF energy began with the theoretical work of a guy named Maxwell, who put some brain thought into some theoretical thinking that was then experimentally verified by another guy named Hertz. This was around 150 years ago. What came out of this was a way to describe, together with Maxwell's equations, which you see here on the screen, and the wave equation, they created a set of partial differential equations that could be used to, in a theoretical manner, describe radio wave propagation. Now, things become really complex, and it's not really useful unless it's really highly idealized cases. So what we do is we simplify this. We simplify this a lot. So back to the example with a transmitter. So we have a transmitter, we have an antenna. We feed this antenna with a, let me try to pronounce this, sinusoidally. Jesus, it's a difficult word. Really difficult. Let me try again. Sinusoidally. There we got it. Never saying that again. Varying current that creates an electromagnetic wave, which is propagated through the air. Now, this electromagnetic wave contains two fields, electric and magnetic. This propagates through the air. It can propagate through vacuum, doesn't need any medium to travel in, and the energy is actually decreasing significantly as soon as it leaves the antenna itself. This is transmitted. We have some sort of frequency. Frequency means the wave you see up there. So the wavelength is defined between two different peaks in this wave. And it's inversely proportional to the frequency. And we'll see later why that is important. So we have some sort of wave being sent, being received in another antenna. The electro part of this electromagnetic wave is generating a current in the receiving piece of metal. And this is how we get the data into the device. And actually, that antenna over there is not just transmitting a wave. It more or less looks like a donut in reality, right? It's transmit omnidirectional. So let's talk about something I'm a little bit more passionate about. So the basic physics of electromagnetic waves comes in so many flavors that it's poetically stated, referred to as Maxwell's rainbow. So if we take a look at this, this is the electromagnetic wave at different frequencies and what kind of applications and meanings they do have. At the far left corner, we do have sound. Admittedly, sound does, and voice, do need a medium to travel in. It's compressing the air, so it doesn't really apply in this case, but it's often used because it uses the same theoretical models as electromagnetic waves. Then we have the fantastic radio spectrum, where we have some really nice abbreviations. So starting from the left, very low frequency. We then have low frequency, medium frequency, high frequency, very high frequency. Guess the next one? Ultra high frequency, super high frequency, and extremely high frequency. I can imagine that these weren't named at the same point in time, right? No. Then on the spectrum we have IR, so it can be used in heat mappings and things like that. We increase the frequency even further, we get into the visible light. That's how we interpret colors, because those wavelengths are so small that they can be captured by, I don't know, the mechanisms in our eyes. Move on to UV frequencies, X-ray. Now we have such fast frequency and so small wavelength, so we can penetrate tissue, flesh, but not the skeleton, which is why X-ray becomes a very useful technology for medical uses. Gamma rays, starting to get down to atoms, quantum physics, starting to being able to modify cells in our bodies, which is why it's radioactive. And gamma rays, we don't want to go there because that shit blows up stuff. So it's pretty dangerous over there. I've added a banana for scale here. For UHF band, we have the wavelength around 12 to 15 centimeters. And why is that important? Why is the wavelength and frequency important? It actually boils down to the size of the antenna that we're going to use for this specific application. And I'm going to show you a bit later why. Some other things for scale, we have atom scales. That's actually an H2O molecule. We have a cell. And obviously, we have the Death Star at 120 kilometers of diameter. So that's some reference for you guys. Now, we're going to talk about the radio spectrum, right? And in these purple boxes, this is where we have the normal, commonly referred to as the radio technologies that we use on a daily basis. So from marine applications up to what I refer to in this talk as the IoT spectrum of things. This is where we have 300 megahertz up to 3 gigahertz. It's probably chosen because the design is convenient and we actually can use antennas, which is in a good, sizable manner. Antennas. Not a very hot topic, right? It's basically a piece of metal that can look very differently. The purpose of the antenna is simply to transfer the electrical signal to an electromagnetic wave. It's simple as that. So we have a few different examples here. We have a simple dipole antenna to the left. That's the one that creates the donut of electromagnetic waves in all directions. We have a Yagi antenna, which is sort of a way to create a lobe in a certain direction. So in terms of creating solutions that should only be available in a certain path, example for along roads, things like that, we have different types of antenna to create directivity. And we have the PCB antennas. Those are the ones that are printed on the solution itself. So if you have a circuit board, those are the ones included directly in the design. It doesn't need an external antenna. And there's a lot of magic behind that one. Actually, if you calculate, this antenna, the PCB antenna, is using 2.4 gigahertz, which means that the wavelength is 12 point something centimeters. But that antenna isn't 12 point something centimeters. In fact, that antenna, as we look at right there, it has a width of around 2.5. The total that we see there has around 3, which is a quarter of 12. So it's essentially a quarter wave design. And in fact, the other element is actually reflected in the ground layer to create a dipole antenna. Right? Starting to get complicated, right? I'm not going to go deeper than that, I promise. So we have different type of antennas. In reality, they're just piece of metals, but have a huge impact when it comes to design and when it comes to getting real performance. Do you remember the antenna gate problem that iPhone had? The idiots over there, they actually created a phone with the antenna placed outside without isolating it. So what happens is you actually shortcutted 2 different antennas and created a new antenna of those 2 previously that was sitting there. So the whole radio forum, I don't even know if it's a radio forum, but everybody was laughing that was into those kind of things, I guess. So these antennas, they send off a signal. How do you know what the signals is? How do you transfer that into zeros and ones? How do you know what the data is? Then we come into something called modulation. Modulation is a way to represent a 0 or a 1 over the air. So we have some different simple examples. So we can either have amplitude modulation. Amplitude is the height of the electromagnetic wave we're sending. So either we have a signal or we don't. Over time, represents ones and zeros. We can change the frequency in the signal over time, or we can change the phase. That's 3 different, very basic high-level stuff. And in reality, that's actually the AM and FM is something you might recognize from the old radios. Today, we don't really use these in real applications. We use more complex modulations that represent multiple states over time to fit more data into the electromagnetic wave. Okay, so let's take a look at some mathematics, right? It's Friday afternoon, and you've been chilling for a couple of days, right? So we have a transmitter, we have a receiver, we have the transmitter sending off some sort of power from the device. We have a gain to even further increase this signal through the antenna out. We have something called path loss. That's the big red triangle in the middle. That's where stuff happens in the air that we have no control over. We further add a gain to the signal when we receive it, and we have the receive signal. Now, we can take Maxwell's equations together with the wave equation, and we can simplify stuff. Now, this is the simplified stuff. So we have the freeze equation up there. We have the signal-to-noise ratio. We can derive the expectations out of this ecosystem. I'm not going to do that. What we're looking at down here is the link budget, the equation for link budget. I want to do things even more simply because this doesn't even make sense to me. So what we do is that we have the output power. This is a device that transmits a signal with a certain energy. This can be interpreted as a person talking. Is the person talking loud, or is this a really old, grumpy grandpa whispering? At the receiving device, we have sensitivity, which is how good can we hear, right? Is this a young fellow? Is it a really old grandma sitting trying to hear? So, simple as that. Link budget is what it sounds like. It's the budget we have in terms of the link quality. So, link budget is sensitivity minus the output power. Why is this useful at all? Well, the link budget is one value that can be used to compare different types of solutions, different type of vendors. It says something about the expected performance and range with this product. This not only means that you can expect a certain range, it means that if you have a really good link budget, it means that when two devices are close in a very crowded environment, for example, if you're out here trying to speak to your colleague and there's a lot of fuss around, if you have really good link budget, you're not going to have a problem with coexistence, because you're screaming to each other, as an example. So link budget is very good in terms of comparing stuff. Now this comes in dBms and dBis and dBs, which are units to express certain energies. Just to give you a little bit of thought when it comes to power, energy, I put up this nice little visual representation. So we talk about output power. So an FM radio station has really extremely high energy being pumped out to all the different radios, us being able to receive music and stuff like that. Going down a bit, we have microwave ovens. Maybe we think about them as simple magic mechanisms that heat food, but it's doing it with microwave signals, blasting dangerous, to some extent, signals, electromagnetic waves onto the things we want to defrost or heat up. We go down to amateur radio stations or amateur radio. We're getting closer to 0 dBm, which is where we have around 1 milliwatt of out effect from these devices. That's actual energy being sent out. Phones, obviously, we hold them to our heads. And the direction that the energy goes out in terms of the radio is actually the other direction, which is very good for us. But you should probably think about that when you are, well, I was going to say when you are sleeping, but in the end it doesn't really make sense at all. So just forget about that part. That's how it goes when you try to improvise on stage. Anyhow, moving on. So we have the Wi-Fi at home. Has a kind of high output power. IoT nodes is sort of around 1 milliwatt. So in terms of what we're transmitting, we're able to do that at a very low energy budget. In terms of being able to receive the signal, we're looking at the sensitivity, which operates on minus dBms. And I talked about that you lose a lot of signals. So if you send out an electromagnetic wave at 0 dBm, you lose energy directly. So if you go down to minus 50 dBms, minus 60 dBms, if you go down below 100 dBms, the receiver might not even be able to pick up that signal. So this relates to the TX output power and the receiver capabilities in terms of sensitivity. In terms of what you power these devices, obviously power supply, so mains, USB, this is what you use to power these huge devices that needs to direct these huge amounts of energy. Getting down to handheld devices, we rely on batteries We rely on lithium ions, small coin cell batteries, as I already mentioned. We're starting to see really cool innovation when it comes to energy harvesting, being able to power these devices on solar energy, kinetic energy, types of energies that we can get from the nature. While I'm at it, I want to mention a few things about range. I mentioned range already. There are a few factors when it comes to getting a good range on a signal. I already talked about the output power. Of course, the more you boost out from this device, the better range. And the better sensitivity you have on the other side, the better range. However, there are a couple of things in between that affects the signal. The first one is frequency. Which frequency are you using? Low frequency typically means that you can send longer. High frequency means that you can send shorter. Antenna performance. As I already mentioned a bit, if you have a really crappy antenna design, you may have significant problems. So if you have a heart rate monitor connected to your phone that you have on your back, you have to penetrate the entire body. And typically it operates on 2.4 gigahertz, which doesn't penetrate water at all. We are made up of 60% water. So if, for example, antenna performance is really bad, somebody's done a really bad job at that, you might actually not get the signal to your phone because you might have too much water in between, I guess. So there's actually some real cases out there with products having really bad performance just because they made a crappy design with the antennas. Anyhow, coexistence. Devices need to be able to coexist in the same room. There's a lot of people in here that has their phones on, connected to the Wi-Fi here. You have some smartwatches, you have the laptops. So these devices need to be able to coexist. And they're actually in here is just a lot of retransmission going on at the same time, all the time, because we're so many here. You've probably been on the subway trying to listen to music on your Bluetooth headset, and the noise starts flipping out. That's because of coexistence problems and a lot of energy, RF energy in the air in general. Environment. The environment has a huge effect on RF signals. In fact, if you are in a field, right, you put up two devices, you have what is referred to as line of sight, which means that you will have some reflections with the signal on the ground, and at some frequencies, you might actually have reflections on the cloud and the ionosphere, but that's out of this discussion when it comes to IoT, but you have some sort of reflection. But in the end, you have line of sight. So you have very little problem with the link. So this is typically how you characterize a product to see what kind of range it has. You put it to the ideal case. If you add some water to this, as I already said, water is a big problem for 2.4 gigahertz. Then you have some huge problems. And also, as I said, human people, we are huge sacks of waters walking around disturbing the 2.4 gigahertz signals, truth be told. What about cities? All of a sudden, we have huge buildings in the way for us. We have cars, metal cars, moving metal cars. So there's a lot of problem in the city when it comes to multipath fading, signals that are affected by constructive fading, destructive fading. So there are a lot of physics on how things impact the electromagnetic wave. Now, we don't see that on a daily basis, but it happens all the time. So we solve this by using spread spectrum techniques, error correcting codes, antenna diversity. So there's a lot of fancy, efficient ways of going around this. But one might think that, well, if there's a problem with getting the signal through, why not just, plug this device into a wall and just maximize the out effect, sending this with 100 dBms, just blasting away all the products. Well, we can't, because obviously there are regulations in the world. So if we're using sub 1 gigahertz, so that is frequencies below 1 gigahertz, we're bound to follow national regulations, and it's different frequencies in different regions in the world. Today, it's not so much a problem since we have software configurable radios. We can just flip the frequency by a little bit in the design itself. But it was a problem. It was a problem, and it might be one of the reasons why all the consumer products, the Wi-Fi is operating on the 2.4 gigahertz band, because that is open worldwide. And you know why it's open worldwide? Because of this little guy, the microwave oven. Through a very thorough process, it was decided to open up the 2.4 gigahertz band all around the world so we could sell and buy microwave ovens. And in fact, if you go home and you have a microwave oven and you put it on a max effect, try to do a download test on your Wi-Fi, through your Wi-Fi router, if you don't use 5 gigahertz, obviously. All right, I've talked a little about the dark arts of wireless communication. Now, as I said, it wasn't that dark. It was really dark a couple of days ago, but then I decided that I'm going to NDC and not an IEEE conference. So I tried to make it a little bit easier to understand concepts. But what I've talked about until now hasn't really been things I want you to take with you away from here. What I'm going to mention now and what I'm going to talk about is a little more hand-fast stuff. And that's the stuff that I want you to take with you after this session. Yeah, I don't even know if hand-fast is an English word. I'm a Swede, so I don't even know if it's a Norwegian word either. But I live here, though. Okay. This has been shown 3 times on this conference already this week. And it's funny because it's true. I mean, this is still happening over and over again when it comes to wireless protocols. But the only difference is that these competing standards doesn't really compete. They're not invented to take, well, some of them are invented to take over other wireless standards, but some of them are just uniquely standardized for their specific case. So we're going to take quick look at some concrete examples. So in a spectrum of having wireless communication solutions in really close vicinity, so short-range networks, we do have the usual suspects. We have NFC, which is used for really small transmitting distances. We have Wi-Fi, that we all know of. We have some industrial home automation solutions. Thread, Zigbee, Z-Wave is a very, very common solution for hobbyists to create their smart home that you can find on Clas Ohlson and other types of stores. It's not that robust, though, to my experience. And we have Bluetooth. Bluetooth is one of those standards that is like trying to take over all the other protocols. They're trying to do all kinds of stuff, mesh, long range. They're not necessarily doing a very good job in taking over some of the segments. They are in the quadrant of wide area network, although they only have 1,600 meters as a maximum range, which doesn't even come close to the other types of standards that we see in the IoT spectrum, which is utilizing licensed cellular base stations, solutions that we get the really long-range applications running on. And 2.4 gigahertz, it's open worldwide. We get a lot of throughput through it, but it can't penetrate walls. Now that is workaround through mesh solutions, so jumping around corners, sort of. For sub-1 gigahertz solutions or long-range wide area networks, we have the problem of the regulations, and we can't really send much data today on these type of solutions. And to be fair, all of these solve their own problem, so there isn't one to carry the trophy. They're all useful for their own use cases. The best part is that the wireless MCUs, the solutions that come out today, can actually operate multiple of these in one chip. So that's a very pro. But how does it work in practice? So a practical example, you have a Wi-Fi router at home that is using one of the common Wi-Fi channels, 1, 6, and 11, or maybe you have actually configured it to use some other channels because you're smart enough to understand that you should do that. Then you have your fitness trackers that operates on 2.4 gigahertz. This is a Fitbit. It uses Bluetooth Low Energy. Bluetooth Low Energy was created to try to avoid interference with Wi-Fi. So what they did was that they created these 3 channels, 37, 38, 39. We want to place these at the occasions where we don't think the Wi-Fi is going to be operating on. And we use those channels to say, hey, here am I want to connect. Hey, here's some data, and so forth. And then a device can connect, synchronize, and then use the other channels to frequency hop. And if we send a signal on a channel over Bluetooth Low Energy, which is busy with Wi-Fi, the signal doesn't come through, but we try on the next frequency hop on another channel. So it's sort of jumping back and forth, trying to send on different type of channels. So that's a way to avoid or improve coexistency amongst wireless products. Everything works perfectly until this asshole arrives into the picture again. I don't have a microwave oven at home, by the way. Okay, practical example for you. Sorry about the product placement. This is a little small device, so you as a developer, you want to add some sort of connectivity to your product. You buy this sort of development platform from a provider. And just to make sure I'm not here to do marketing from TI, I also have a kit from Nordic Semiconductor here as well. Anyway, back to the more awesome solution. Okay, so we have some sort of wireless MCU. Now this is a multi-purpose device that has processor, it has RAM, flash, it has memory, it has a radio front end, is able to operate on multiple different types of protocols. We have some sort of antennas. We've talked about antennas. This one has the weird inverted F antenna that is mounted directly into the printed circuit board. The screen is a bit dark, so you don't see it, but it's there, I promise. We also have a micro SMA connector if you want to add other types of antennas to evaluate different solutions. We have a crystal oscillator that is typically clocking the device. This is a tick. That is what brings the processor to the next step in the execution. We also have a sleep crystal on the backside, which is why the device can go into sleep mode and then wake up later to send off a signal. That's how you get low power consumption. And a lot of sensors on it. So typically one takes this type of solution, start evaluating, trying out things, and you add the solution to your existing products or your new product. And it's important to test things out in the real world because it doesn't matter if you do theoretical calculations. That's why I just scrapped all the equations. But in the end, it only matters in what environment you're actually going to test this out. Will it actually work? Is there a lot of other devices, other people moving around? I mean, there's a lot of things to consider, right? So you take this device, you program it in some weird way, and you get it to send a packet. What is a packet? I mean, we talked about electromagnetic wave. We talked about modulation. Modulation is zeros and ones and so forth. But how did the radio know that, hey, here's a 0, I want to grab this? Is there something more? Then we have packets. So a packet being sent from this device might be a Bluetooth Low Energy beacon packet. This is simply a packet that is being sent. So we have a preamble. This is what the radio syncs to. It recognizes the access address, and then it's like, hey, this is actually a Bluetooth Low Energy beacon. Let's continue to listen. Oh, here's a PDU. And then we have a cyclic redundancy check in the end, and that's what we use to calculate back and see that this was the actual packet that was sent from the transmitting device. We're looking into the details, and we find in the bottom some sort of useful data. Now, if this is a beacon, this is typically a static one that is defined by Apple, if we have iBeacon, or Google, if we have Eddystone, or Altbeacon, if we have radios networks. So there's different standards here as well when it comes to formatting. Or it could be just saying, hey, I want to connect, I have more data to share. Or it could be the temperature value or something else. that is sent in this packet. And if you compare this type of packet with a Wi-Fi packet, there's a huge difference. In Bluetooth Low Energy, in many of these IoT protocols, we try to minimize the amount of time the device is in TX. Because every microsecond the device is in TX is going to consume energy and heat up the device to even consume more energy. So we want to minimize the amount of transmissions we actually do. And that's why we have just a few bytes being sent over in the air. And there's a lot of proprietary protocols where we try to reduce this as well to increase the battery lifetime. So when we send off these packets, we typically have some sort of topology, right? We're sending this packet to somebody else. So often we have some sort of master device that is the dictator that receives the packet or sends the packet, or we might have a bidirectional communication. And by bidirectional, I don't mean full duplex. That doesn't really exist in wireless communication, at least not that I'm aware of. We have half duplex, so we time divide the communication. So we have some sort of point-to-point solution, or since we do have a lot more capabilities in these small embedded devices, we usually have room for star topology, even though we were just aiming for point-to-point topology. So this is the type of topology you see in smartphones, where you're connected to multiple types of, that could be smartphones, your fitness tracker, I don't know, connected shoe, whatever you have. Or it could be some other type of topology where one needs to be the dictator to controlling all different nodes. I mentioned mesh. Mesh is where you have one, or actually you have more like a hierarchy of one dictator and small mini dictators. In a mesh solution, that's the one that is most commonly used in home automation in some industrial applications where you have Zigbee, Z-Wave, Thread is coming there as well. And when it comes to developing solutions for IoT, I've seen that there's been a lot of talks at this conference talking about some really cool applications when it comes to embedded devices and being able to use high-level programming languages. Now, if you have a device, an embedded device, like this one, or like any other IoT-related wireless MCU, last year, the most popular and indicated programming language was C. C is the most widely known programming language for embedded devices. It was also indicated that we have some other up-and-coming standards like Java, C++, or Python. Now, this year, we've seen a lot of cool implementation using JavaScript. I don't know if I believe that stuff, to be honest. I need to look into that a bit deeper. In the end, it's translation to translation to translation, and then you end up at assembly language, which is machine code, right? But from a software perspective, you can use abstractions and allow high-level programming, but in terms of protocols, in terms of Thread, Bluetooth Low Energy, Zigbee, you typically get a full protocol stack built up as a library, and then you develop your application to an API. So the development in terms of software becomes a top-level design on the application, and with the new multi-protocol solution that is coming out, you can actually develop applications to interact with different types of protocol stacks that can create more dynamic implementations. So, I've talked about things around wireless communication. I didn't go as deep as I intended. I've tried to stay focused. Now, I know that this talk is called How to Become a Wireless Connectivity Ninja 101. Now, there is an extensive list, and I don't expect you to remember this list. I'm expecting you to remember that this list exists. So these are the types of things you need to consider, need to have thought for when it comes to creating IoT products with wireless communication. So, bear with me. The first one is the environment. As I talked to you about, it's all about the geographical location when it comes to regulations, when it comes to is there going to be people around, metal objects, things like that need to be considered. Materials, objects, so forth. The second one is size. How small is this device going to be? Is it going to be small like the coin cell battery itself? Do we need to optimize everything to size? What material, which packaging are we going to have this device? What about the antenna? I mean, if we're sending something off with 27 megahertz, we have an antenna which would be 3 meters with a quarter wavelength antenna. There's a lot of things to consider when it comes to the size of the actual product. Cost. Cost is a very important thing. I mean, if you're going to create a consumer product that should not work in 1 year, maybe there's trade-offs, shortcuts you can do. But in general, you want to do robust solutions, right? So cost becomes an interesting topic where you need to pick high-quality stuff. I'm not going to stand here and say what is not high quality and what is low high quality, but it's definitely a parameter to consider. Data. How much data are you going to send in this product? Are you going to send 1 byte a month to just represent the state of this product? Are you going to do over-the-air transfers to upgrade the firmware on the device? Do you care about latency? Is time a critical requirement for this product? So there's different type of things to consider when it comes to that. Power. I already mentioned this. Will this require mains power, continuous feed of power? Can it be operated by batteries? Or can we afford to just having harvesting solar power to wake this device up and send off a message? Serviceability. Unlicensed, licensed. What do we do, for example, if we release NB-IoT product? Because then we are bound to actually rely on the cellular base stations being there. Or if we design a Bluetooth Low Energy product, it's dependent on an application that is running on the smartphone. So we need to think about concepts beyond CAPEX, so capital expenses. We need to think about the operational expenses when it comes to maintaining this solution as well. So the wireless part comes into this picture as well, choosing the right technologies. Processing. How much processing will we do on our device, really? So there's a lot of ideas about just sending off the raw data up to the cloud, and then we can process the stuff over there. However, in terms of time budget with the RF communication, maybe you shouldn't send all the data. Maybe you should just process some of the data locally, filter, and be able to just pass on the really important data to keep the power consumption low. Topology. I mentioned this. Which kind of topology should we be using? Point-to-point, mesh is a good consideration to have, as well as security. So for confidentiality, you need encryption to be able to make sure that your device or the data is protected. You have authentication, being able to protect yourself against man-in-the-middle attack. You have integrity, making sure that the packet is intact and nobody fills with it. You have privacy, making sure that nobody can track this device, and so forth. And authorization, which is being able to give somebody access or not access. And finally, availability. Is this product, is this solution, is this technology been proven? Has it been deployed? Has it been deployed for years? Is it new? Is it disruptive? Is this changing the way we should operate? Okay. Let's wrap up. There are 3 things I want to just share with you that I want you to take away with you. The first one is the battle of standards. So there is a lot of competing standards. There is a lot of various different services, applications, platforms. Don't get lost in all these different solutions. Try to refocus on the actual problem. Try to figure out if that is a good solution. Is that available in your geographical area where you're going to deploy the product and so forth? Use a hackathon as a method to evaluate that specific solution for that problem statement. Secondly, RF is black magic. Now, I didn't even go into how these electromagnetic waves behave on transmission lines and things like that. So, but believe me, RF is black magic. There's a lot of things that cannot be explained, right? Just believe me on that one. So what I want to say is you can do theoretical calculations to make expectations to help you, but in the end, you have to test it in the real world. You have to test it in the real environment to know and understand if this is going to work. So you put the test into a pilot project. You run the potential solution over days, weeks, months to see if it actually works. Then you can verify it towards theoretical calculations around the solution. And finally, I have to say, everything becomes software configurable. So software is key. It's one of the most sought after knowledge that you can have on the market today. And it also applies to these type of solutions, radio communication and wireless connectivity and so forth, because these become software configurable. Everything becomes software configurable. You can change the protocols on the fly. You can do over-the-air updates. All that is software. So hardware is becoming a commodity. Yeah, there's going to be a few people who makes the hardware, but the innovation, creating the value, is done by software. All right, almost the final slide. Friday afternoon. I just want to share one of the nicest citations I know of. This is Thomas Edison. And he said, "I have not failed. I have found 10,000 ways that don't work." So my message is keep trying, keep doing, because the technology is advancing faster than our ability to adapt. So there's no time dwelling in different kind of protocols and what not to do and so forth. Just do it, right? Okay. With that, I'd like to thank you. Please connect to me and follow me on LinkedIn. I do not have Twitter, WhatsApp, whatever, what's not, and all that. So please use LinkedIn, either to follow me or to connect to me. I usually release a couple of articles a year. Okay. Thank you.